1967, Cambridge University. In the quiet hum of a research laboratory, a young graduate student named Jocelyn Bell Burnell meticulously reviewed reams of paper charts, endless lines tracing the faint whispers from across the cosmos. For weeks, she had been scanning these records, searching for the telltale signs of distant quasars. But then, an anomaly appeared. A persistent, curious bit of scruff, as she called it, a repeating pulse that defied all known explanations. This wasn't a quasar. This was something entirely new, a cosmic lighthouse later named a pulsar, spinning with an almost impossible precision, each pulse a precise cosmic clock tick. This monumental discovery, born from human diligence and a touch of serendipity, stands as a testament to our innate ability to find patterns, to discern meaning from the chaos of raw data. Our brains, honed by millennia of evolution, are magnificent instruments of recognition, wired to spot the unusual, to connect disparate dots. Yet, this very strength also reveals a profound limitation. For every pulsar glimpsed, how many other, equally revolutionary signals might we have missed? Our minds, while powerful, are also fragile. They are easily overwhelmed by sheer volume and dangerously susceptible to cognitive biases, like confirmation bias, the tendency to see only what we expect to see, filtering out anything that doesn't fit our preconceived notions. Today, the universe is no longer a quiet whisper on chart paper. It is a roaring deluge of information. Consider the Vera C. Rubin Observatory, nestled high in the Chilean Andes. Once fully operational, this colossal eye on the sky is projected to generate over 20 terabytes of data every single night. To put that into perspective, that is the equivalent of more than 4,000 high-definition movies, streaming simultaneously, 24 hours a day. This torrent of information far, far exceeds the capacity of thousands of human astronomers combined. Imagine an army of experts, all attempting to manually sift through this digital ocean. It would be an impossible, soul-crushing task. This isn't merely a problem of scale, it's a fundamental challenge to human perception itself. We understand this challenge from insights gained far from the world of telescopes. Think of the psychological concept known as inattentional blindness, famously demonstrated by Daniel Simons and Christopher Chabris in their 1999 invisible gorilla experiment. Volunteers were asked to count basketball passes on a video. So engrossed were they in their primary task that nearly half of them completely failed to notice a person in a gorilla suit walking directly through the game. An extraordinary event, right in front of their eyes, simply did not register because their attention was focused elsewhere. Now, apply this chilling insight to the cosmos. In the vast, intricate datasets streaming from our most advanced observatories, how many invisible gorillas are parading right before our metaphorical eyes? How many crucial cosmic signals, subtle anomalies, or entirely new phenomena are being overlooked simply because we are not specifically looking for them, or because they do not fit our established understanding of the universe? The realization that we could be blind to the most significant discoveries, not for lack of data or sophisticated instruments, but for inherent limitations in our own perception, has become the primary driver for a revolutionary new approach. We are, in a sense, the blind watchmakers of the universe. We meticulously assemble our picture of reality, piece by painstaking piece, using the tools we possess. our senses, our intellect, our intuition. But these tools, remarkable as they are, have reached an evolutionary limit when confronted with the universe's true complexity and data density. To perceive the cosmos as it truly is, to uncover its deepest secrets, we now need something more. We need a new form of sight, an extension of our very minds, a necessary prosthetic for human understanding. This is where artificial intelligence enters the cosmic stage, not as a mere data processing machine, but as a revolutionary new way to finally perceive the invisible gorillas of the cosmos. The human eye, a marvel of evolution, captures light and transforms it into understanding, allowing us to navigate a complex world. But could we replicate that profound, almost mystical process? Could we build an electronic equivalent of an optic nerve, a digital visual cortex, capable of sifting through the universe's vast imagery? This was the audacious question that marked the conceptual birth of artificial intelligence as we now understand it. We journey back to the year 1958, to Frank Rosenblatt and his team at the Cornell Aeronautical Laboratory. In that era, the very notion of a machine learning was science fiction, yet Rosenblatt unveiled the perceptron. This pioneering creation was an early neural network, a rudimentary electronic system designed to mimic the fundamental function of a biological neuron. It was a bold, unprecedented attempt to teach a machine to recognize patterns, to learn from data, laying the groundwork for the astonishing advancements we witness today. The perceptron, with its simple layers of interconnected nodes, was the earliest ancestor of the sophisticated digital eyes now scanning the cosmos. Fast forward to the present, and the direct descendants of Rosenblatt's early work are the workhorses of modern astronomical AI, convolutional neural networks, or CNNs. These complex architectures function as a kind of digital optic nerve and visual cortex for our most powerful telescopes. Unlike traditional computer algorithms which demand explicit instructions, for example, find round objects of a certain brightness, or identify lines at this specific angle, a CNN learns through experience. It is not programmed with rules, it deduces them. This is the crucial, almost magical distinction. Consider how a child learns to recognize a cat. No one provides a precise set of rules for catness: 4 legs, 2 ears, a tail. Instead, a child sees millions of examples: fluffy cats, sleek cats, black cats, orange cats, cats sleeping, cats playing. Through this vast exposure, the child's brain constructs an internal model, an understanding of what constitutes a cat, recognizing features that might be too subtle for explicit description. A CNN learns in precisely the same way. It processes countless images of spiral galaxies, elliptical galaxies, or planetary nebulae, internalizing the defining features of each, building its own intricate neural pathways to classify cosmic phenomena without human instruction. This is where a truly revolutionary citizen science initiative stepped onto the stage: the Galaxy Zoo project. Initially, this ambitious undertaking invited hundreds of thousands of volunteers from around the world to manually classify galaxies captured by the Sloan Digital Sky Survey. They sorted through millions of celestial images, labeling them as spiral, elliptical, or irregular. What began as a grand exercise in human collective intelligence eventually yielded something even more profound: a massive, meticulously human-labeled dataset. This colossal collection became the perfect textbook for training the emerging convolutional neural networks. The impact was immediate and transformative. A task that once consumed thousands of hours of painstaking human labor, stretching across years for comprehensive surveys, could now be completed in mere minutes by an AI. But the benefits extended far beyond mere speed. More importantly, the trained AI began to recognize subtleties and transitional forms of galaxies that even human experts, with all their experience, might debate or categorize inconsistently. It unveiled a nuanced understanding of cosmic structures, revealing a spectrum of galactic evolution that our biases or limited processing power might have otherwise obscured. This powerful capability underscores a fundamental truth. AI in astronomy is not some mystical force. It is a sophisticated form of statistical pattern recognition, directly inspired by the very neural structures we use to comprehend the world, now exquisitely applied to the torrents of data streaming from the deepest reaches of space. The universe, in its boundless expanse, is not always a symphony of clear signals. More often, it is a cacophony, a vast ocean of cosmic static where the most profound discoveries might hide as mere whispers. Consider this: what if the universe itself were trying to tell us something, but its voice was lost in a hurricane of noise, a faint, repeating beat buried deep within the relentless static? This is the fundamental challenge that now faces astronomers, moving far beyond the more straightforward task of classifying images of galaxies. Here, the quest is for the ultra-faint, for signals so elusive that they are the cosmic equivalent of hearing a whisper in the heart of a storm. For years, one of the most enigmatic whispers has been the fast radio burst, or FRB. These are millisecond-long blasts of radio energy originating from deep space, so brief and powerful that their very existence challenges our understanding of extreme astrophysical phenomena. Their true origins remain one of the biggest mysteries in the universe, an unsolved riddle etched into the fabric of spacetime. The first of these elusive signals, named FRB010625, was not actively sought out, but found by sheer chance. It was the year 2007, and two astronomers, Duncan Lorimer and David Narkovich, were meticulously reanalyzing archival data collected years earlier by the colossal Parkes Observatory in Australia. Sifting through old records, a persistent, unidentifiable pattern emerged, a flash of energy that lasted barely a blink of an eye, yet carried the signature of an event of unimaginable power, billions of light-years away. The manual discovery of that first, fast radio burst was like plucking a single grain of sand from a desert the size of Earth. For many years thereafter, finding more of these signals was an excruciatingly slow and painstaking process. Astronomers spent countless hours sifting through terabytes of raw radio data, a task akin to searching for a needle in a haystack, only the haystack was expanding exponentially every second. The sheer volume of incoming information from the cosmos threatened to overwhelm even the most dedicated human minds. Yet, a new generation of telescopes, armed with a revolutionary form of intelligence, began to change everything. Enter the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, radio telescope, nestled in British Columbia. This extraordinary instrument is not merely collecting data, It is processing it in real time, sifting through a torrent of information equivalent to the entire global Internet's traffic several times over, every single day. This astronomical data deluge is handled not by human hands, but by sophisticated artificial intelligence systems. These AI algorithms are specifically engineered to identify the unique, dispersed whistle of an FRB as it travels through the vast intergalactic medium. As these radio waves traverse the cosmos, they are scattered and stretched by interstellar gas and plasma, causing the higher frequencies to arrive slightly before the lower ones, a distinctive signature that acts like a cosmic fingerprint. The AI systems employed by telescopes like CHIME utilize a specialized type of neural network known as a recurrent neural network, or RNN. Unlike their convolutional counterparts, which excel at recognizing patterns in static images, RNNs are designed to process sequential data, making them perfectly suited for signals that evolve over time. They can learn to predict what comes next in a sequence, and more importantly, to spot deviations from expected patterns. This capability allows them to meticulously track the subtle, dispersed arrival of an FRB's frequencies, distinguishing it from the ceaseless background noise of our own galaxy and distant cosmic sources. It is a level of vigilance and processing speed that no human team could ever hope to match. To truly grasp the genius behind these systems, one might look to a seemingly unrelated yet historically critical field: submarine warfare during the Cold War. In that high-stakes arena, scientists and engineers were faced with an equally challenging problem: distinguishing the faint acoustic signature of an enemy submarine from the overwhelming cacophony of the ocean. The creaking of ice, the calls of whales, the distant rumble of ships, all conspired to mask the almost imperceptible hum of a hidden vessel. Over decades, sophisticated signal processing techniques and early forms of artificial intelligence were developed to isolate those specific, telltale patterns in an immense, noisy environment. The very same principles of identifying a faint, sequential pattern against a wall of random interference, refined over decades of geopolitical tension, have now been adapted and advanced to unveil the universe's deepest secrets. This reveals artificial intelligence in a new and critical light, as a tireless sentinel, an ever-vigilant guardian of our cosmic senses. It possesses the superhuman patience to monitor vast datasets in real time, to tirelessly sift through the overwhelming noise of the cosmos, searching for the rarest and faintest ghosts that would otherwise be lost forever. It is the silent, indefatigable hunter, tracking down anomalies and whispers that, without its unwavering attention, would simply vanish into the cosmic static. The human mind has long been driven by a singular, audacious ambition: to not merely observe the universe, but to build it, not with bricks and mortar, but with equations and theories, to craft working models of reality itself. We have peered through telescopes, listened to the cosmos's whispers, and sifted through the noise, piecing together the story of creation. Yet, the universe remains a riddle of staggering complexity, its deepest secrets locked within phenomena too vast or too subtle for our direct comprehension. How, then, do we truly understand the forces that shaped everything, from the smallest atom to the grandest galaxy cluster? The answer, surprisingly, now lies in teaching machines not just to see, but to dream up new universes. This dramatic shift from observation to creation began in 2014 with a revolutionary idea from a researcher named Ian Goodfellow. He introduced a concept so profound it has reshaped fields far beyond computer science: generative adversarial networks, or GANs. At their heart, GANs are a masterclass in collaboration through competition, a kind of digital duel between two distinct artificial intelligences. One AI is known as the generator. Its task is to create. The other is the discriminator. Its role is to critique. This isn't about conjuring deepfakes or manipulating reality for trivial purposes. It is about forging the fabric of the cosmos, one synthetic image at a time. Consider the generator AI as an aspiring cosmic artist. Its initial creations are clumsy, crude imitations of the universe it is trying to replicate. The discriminator AI, on the other hand, acts as a discerning art critic, an expert judge trained on countless real images of the universe. Its singular purpose is to tell the difference between what is authentic and what is a fabrication. The generator presents its new synthetic images to the discriminator, which then evaluates them. If the discriminator successfully identifies a fake, the generator learns from its failure, adjusting its internal parameters, striving to create an even more convincing forgery. This intricate dance of creation and criticism unfolds over millions of cycles, a relentless feedback loop. The generator continuously refines its artistry, becoming ever more adept at mimicking reality. Meanwhile, the discriminator is forced to sharpen its own analytical skills, pushing its ability to detect the most subtle imperfections. Eventually, the generator becomes so extraordinarily skilled that its creations are utterly indistinguishable from the real thing, even to the keenest eye of the discriminator. This powerful, self-improving engine now provides physicists with an unprecedented tool, a robust, dynamic system capable of simulating intricate what-if scenarios for the very cosmos itself. To truly appreciate this technological marvel, think of it as the alchemist's orrery. Historically, an orrery was a mechanical model of the solar system, a clockwork masterpiece that allowed us to visualize the dance of planets. But this new, digital orrery is far grander. It is a magical, alchemical clockwork model of the entire universe, allowing scientists to experiment with cosmic ingredients and observe the outcomes. For example, a GAN can be meticulously trained on thousands of authentic images of galactic collisions, drawn from the treasure trove of data collected by the Hubble Space Telescope. These are the spectacular, chaotic ballets of galaxies merging, reshaping the cosmic landscape. Once trained, the generator AI can then conjure an endless array of new synthetic images of such collisions. It can craft scenarios that might take millions of years to unfold in real time, or simply generate variations of existing events. The discriminator, having seen the real galactic clashes, diligently scrutinizes each synthetic image, striving to expose the artificial. This iterative process allows astronomers to generate vast, high-fidelity simulations that push the boundaries of our understanding. They can explore how gravity sculpts galaxies during these immense encounters, observing outcomes that would be impossible to witness in a human lifetime. This pioneering work is already yielding astonishing insights. Researchers like Shirley Ho at the Flatiron Institute are at the forefront of using these GANs to generate sprawling, high-fidelity simulations of the cosmic web itself, the vast, interconnected network of galaxies and dark matter that forms the largest known structures in the universe. Traditional supercomputers would require weeks, sometimes even months, to produce a single, detailed simulation of this scale. Yet, with the power of GANs, these same, incredibly complex cosmic models can be generated in mere minutes. This speed is not just a convenience, it is a fundamental game-changer for theoretical cosmology. Scientists can now rapidly test how different cosmological parameters, the fundamental constants that govern the universe, might affect its large-scale structure. For instance, what if the enigmatic force known as dark energy, which is accelerating the expansion of the universe, had a slightly different value? How would that alter the formation of galaxy clusters, or the distribution of invisible dark matter? With GANs, physicists can run countless variations, effectively forging new theoretical universes and then breaking them against observational data. It transforms artificial intelligence into an indispensable, almost magical tool for refining our deepest models of reality, pushing us closer to understanding the true blueprint of the cosmos. What if the vast, intricate tapestry of our cosmos, woven from galaxies and stars, is merely the visible embroidery on a much larger, invisible fabric? For decades, astronomers have wrestled with one of the universe's most profound mysteries: dark matter. It is a substance we cannot see, cannot touch, and cannot directly detect, yet it constitutes over 80% of all the matter in the universe. It is the unseen scaffolding, the silent architect, without which galaxies would simply fly apart, unable to hold themselves together. Its existence is inferred only through its immense gravitational pull, a phantom force shaping the very largest structures of reality. But how do you map something that is fundamentally invisible? The answer lies in a phenomenon predicted by Albert Einstein in 1936, gravitational lensing. Envision a cosmic distortion, a trick of light and gravity. When light from a distant galaxy travels across billions of light-years of space and then passes close to an incredibly massive object, say, a colossal galaxy cluster, a concentration of thousands of galaxies, the cluster's immense gravity acts like a colossal lens. It bends and warps the fabric of space-time, causing the light from the background galaxy to be distorted, magnified, and sometimes even split into multiple images, forming arcs or rings of light. These subtle, ethereal distortions are our only window into the distribution of dark matter, the only way we can see its gravitational influence. They are the fingerprints of the universe's hidden mass. Yet, identifying these cosmic lenses in the endless ocean of observational data is a monumental undertaking. Consider the sheer scale. Modern sky surveys, like the Dark Energy Survey, capture hundreds of millions of galaxy images. Each image might contain thousands of individual galaxies, and somewhere within that glittering multitude, a few scattered, faint, and often subtle arcs or rings might signal the presence of a dark matter lens. For human astronomers, manually sifting through such a colossal database is not just time-consuming, it is an almost impossible task, prone to human error and fatigue. The universe holds its secrets close, and its invisible architect is particularly elusive. This is precisely where artificial intelligence has revolutionized our search for the hidden universe. Pioneering researchers like Dr. Yashar Hazave and Dr. Lawrence Perot-Levasseur recognized the challenge and forged a new path. They trained highly specialized deep learning algorithms to become expert gravitational lens finders. These sophisticated AI systems were fed vast datasets of both real and simulated images of galaxies, some containing the telltale signs of lensing, others being normal. Through this meticulous training, the AI learned to recognize the faint, distorted patterns that signify a cosmic lens, distinguishing them from the overwhelming background noise and countless other galactic shapes. The results are nothing short of extraordinary. An AI can now scan millions of galaxy images from surveys like the Dark Energy Survey with superhuman speed and accuracy, far surpassing any human team. What might take astronomers months or even years of painstaking visual inspection, the AI can accomplish in mere hours, flagging potential gravitational lenses with unprecedented precision. This capability transforms the hunt for dark matter from a slow, laborious crawl into a rapid, expansive exploration. It is akin to a cosmic X-ray machine, revealing the invisible structures embedded within the light of distant stars and galaxies. The underlying principle behind this AI capability has a surprising parallel in another critical field: medicine. Think of an artificial intelligence system trained to detect subtle tumors in medical scans, like MRI or CT images. In both cases, the AI is tasked with a fundamentally similar problem: discerning a specific, often faint pattern of distortion, a minute anomaly, within an incredibly complex and noisy image. Just as a small, irregular shadow might signal a tumor in a lung scan, a faint, stretched arc of light points to a dark matter halo in a cosmic image. The challenge for the algorithms is identical: extracting crucial information from overwhelming visual data. By tirelessly identifying and cataloging these cosmic lenses, artificial intelligence is effectively creating the first-ever large-scale maps of the dark matter scaffolding that underpins our entire universe. These aren't just pretty pictures. They are detailed blueprints of the invisible architecture that governs cosmic evolution. They provide physicists with crucial, never-before-seen data, allowing them to probe the fundamental properties of dark matter, to test theories about its nature, and to understand its indispensable role in the formation and growth of galaxies and the largest structures in the cosmos. These maps are revealing the true shape of our universe, not as we once imagined it, but as it truly is, shaped by forces still largely beyond our direct comprehension. For centuries, humanity has gazed at the night sky, captivated by the distant pinpricks of light, each a sun like our own. The profound question has always been, do they, too, host worlds? While the hunt for exoplanets, worlds beyond our solar system, has become a familiar saga, our journey into this cosmic frontier now takes an unconventional turn. We will not dwell on the transits, where a planet subtly dims its star's light as it passes before it, a method that has revealed thousands of alien worlds. Instead, we delve into a far more audacious and technically demanding quest, directly photographing these distant planets. Consider the immense, almost insurmountable challenge: Trying to directly image an exoplanet is akin to attempting to spot a single firefly hovering next to a blinding searchlight from hundreds of kilometers away. The star, typically billions of times brighter than its orbiting planets in visible light, utterly overwhelms any faint glimmer emanating from its companions. Imagine a celestial stage where the spotlight is so intense it renders the actors invisible. For context, a star like our Sun is roughly 10 billion times more luminous than a Jupiter-sized planet orbiting it in visible wavelengths. Capturing such an image requires astronomical precision and technological mastery, a monumental task that pushes the very boundaries of human ingenuity. To overcome this blinding glare, astronomers employ a suite of cutting-edge technologies. Adaptive optics systems, for instance, rapidly deform telescope mirrors thousands of times per second to counteract the blurring effects of Earth's turbulent atmosphere, effectively creating a perfectly still image as if the telescope were in space. Simultaneously, instruments called coronagraphs are deployed. These ingenious devices act like tiny, internal eclipses, meticulously blocking out the overwhelming light from the parent star, much like holding your thumb up to block a car's headlight. Yet, even with these advanced techniques, a persistent nemesis remains: the residual starlight, or speckle. This optical noise, caused by the diffraction and scattering of light within the telescope itself, creates complex, shifting patterns that can tragically mimic the faint signal of a planet, generating phantom worlds where none exist. This is precisely where artificial intelligence emerges as the ultimate noise cancellation expert. Sophisticated machine learning algorithms are now being deployed to differentiate the faint, true signal of a planet from the complex, ever-present noise of its parent star. One such technique, known as Principal Component Analysis, or PCA, allows the artificial intelligence to learn the characteristic patterns of speckle noise. Think of it like a master musician who can instantly recognize and filter out every unwanted hum and hiss from a recording, leaving only the pure melody. The artificial intelligence sifts through hundreds of thousands of images, identifying the consistent, repeating patterns of the instrument's own optical quirks. Once these noise signatures are learned, the artificial intelligence can then subtract them from the raw data with exquisite precision, revealing the previously hidden, true signal of an exoplanet that might otherwise be lost forever in the cosmic static. But artificial intelligence's role extends far beyond merely spotting distant worlds. It is also helping us unravel the deeper mysteries of how these worlds come into being. This brings us to the breathtaking images captured by the Atacama Large Millimeter Submillimeter Array, or ALMA, telescope in Chile. LMA, a network of 66 high-precision antennas nestled high in the Andes, has delivered unprecedented views of protoplanetary disks, the swirling, dusty nurseries of newly forming star systems. These images are not just beautiful, they are snapshots of creation, showing intricate gaps and ring structures within these disks. These structures are believed to be the telltale signs of infant planets, carving out their orbital paths as they gravitationally sweep up material. However, interpreting these complex structures and understanding the forces that shaped them is a monumental task. The intricate dance of gas, dust, and nascent planets within these disks creates patterns that are incredibly difficult for human analysis alone to fully decode. Here, artificial intelligence is once again proving indispensable. Scientists are now training artificial intelligence to meticulously analyze these intricate gaps and ring structures, to identify subtle deviations and asymmetries that might hint at the presence of multiple planets, or even planets of unusual masses and orbital characteristics. By comparing these artificial intelligence-analyzed structures with thousands of theoretical simulations of planet formation, astronomers can rapidly test different hypotheses about how planets grow and interact within these chaotic environments. This allows them to explore how varying conditions, such as the amount of dust, the strength of the star's magnetic field, or the presence of early massive planets, might influence the final architecture of a solar system. In essence, artificial intelligence is acting as an apprentice to the planet forger of nature, helping us to decode the very rules by which alien solar systems are created, step by painstaking step. It is a tireless collaborator, sifting through the evidence of cosmic creation, pushing us closer to understanding the genesis of worlds, perhaps even worlds like our own. We have long gazed into the cosmos, driven by an ancient human yearning to know if we are alone. For decades, the search for extraterrestrial intelligence, or SETI, has conjured images of powerful radio telescopes patiently listening for a specific, unmistakable message, perhaps a cosmic "Hello, Earth," echoing across light years. But what if the greatest discovery isn't a direct call, but something far more subtle, a whisper that doesn't fit, a note out of tune in the grand symphony of the universe? The legendary science fiction writer Isaac Asimov once famously declared that the most exciting phrase in science is not "Eureka," but "That's funny." This profound sentiment has become the new guiding principle for modern SETI, transforming it from a hopeful but often fruitless search for a preconceived signal into a disciplined, systematic hunt for anomalies. It is a shift from listening for a known tune to identifying any unexpected dissonance. Consider the sheer scale of the cosmic radio spectrum. It is a torrent of signals, a ceaseless flow of information from pulsars, those rapidly spinning neutron stars emitting precise, rhythmic pulses, from quasars, the intensely luminous hearts of distant galaxies powered by supermassive black holes, and from magnetars, dead stars with magnetic fields a quadrillion times stronger than Earth's, capable of unleashing colossal bursts of energy. Alongside these natural cosmic broadcasters, our telescopes are also deluged by the constant, unavoidable cacophony of human-made radio frequency interference, a jumble of terrestrial chatter from mobile phones, satellites, and countless electronic devices. In this overwhelming cosmic noise, how does one even begin to differentiate between the expected and the truly extraordinary? This is where artificial intelligence takes center stage. Projects like Breakthrough Listen, headquartered at the Berkeley SETI Research Center, are pioneering this new approach, not by looking for a specific pattern, but by empowering AI for a much broader, more fundamental task: anomaly detection. Machine learning models are fed vast, meticulously curated datasets that encompass every known natural radio signal and every recognizable form of human-made interference. Through this intensive training, the AI effectively learns what normal sounds like for the universe, constructing a comprehensive baseline of cosmic and terrestrial emissions. Once trained, the AI becomes a tireless cosmic auditor. Its primary task is not to find a specific message, but to flag anything that deviates from this learned baseline, any signal that makes the AI, in essence, say, That's funny. It acts as a digital sentinel, capable of monitoring petabytes of data in real time, recognizing patterns that are too faint, too complex, or too fleeting for human eyes and ears to ever consistently detect. It might be a pulse that's slightly off its expected period, a burst with an unusual frequency drift, or a persistent emission that defies all known astrophysical explanations. This revolutionary methodology is being actively developed and deployed by experts like machine learning specialist Dr. Jerry Harp and his dedicated colleagues at the SETI Institute. Utilizing sophisticated instruments such as the Allen Telescope Array, a 42-dish radio observatory located in Northern California, they are at the forefront of this anomaly-driven search. The array acts as a distributed ear, collecting immense volumes of radio data, which the AI then meticulously sifts through, performing calculations at speeds that dwarf human cognitive abilities. It is akin to a highly specialized librarian who has memorized every book, every article, every single piece of information ever published, and whose sole purpose is to instantly identify any new text that contains even a single sentence, a phrase, or even a punctuation mark that does not conform to the established patterns of human language. This profound shift reframes the search for intelligence itself. It is no longer a romanticized quest for a direct answer, but a disciplined, systematic hunt for any phenomenon, natural or artificial, that falls outside our current understanding of astrophysics. Artificial intelligence, in this context, transforms into the ultimate cosmic archaeologist, sifting through the digital ruins of the universe, not for a specific artifact, but for anything that simply does not belong, anything that hints at a reality far stranger or more intelligent than we have yet dared to conceive. For centuries, the human quest for understanding has been defined by our tools, by the extensions of our senses. From the earliest flint axes that shaped our physical world, to the grand telescopes that opened the cosmos, our reach has always been limited by the instruments we wield. But what happens when the very instrument we create begins to extend not just our physical sight, but our intellectual grasp, our ability to think, to question, and to perceive reality in ways previously unimaginable? This is not a theoretical musing from a science fiction novel. It is the immediate future of astronomy, a profound shift epitomized by a concept born on the chessboard. In the year 1997, after his historic defeat by the supercomputer Deep Blue, Grandmaster Garry Kasparov proposed a revolutionary idea: centaur chess. He discovered that a team composed of a human player and an artificial intelligence, a so-called centaur, could consistently defeat not only the strongest human chess master, but also the most powerful supercomputer operating independently. This was a revelation. The optimal path to supremacy was not through replacement, but through a powerful, almost symbiotic partnership. This very paradigm, the centaur's gaze, is now illuminating the future of cosmic discovery. It is not a world where artificial intelligence replaces the human astronomer, rendering decades of expertise obsolete. Instead, it is a new frontier where a potent human-artificial intelligence symbiosis emerges, unleashing unprecedented capabilities. The artificial intelligence, a tireless, unblinking sentinel, will become the ultimate data processor, capable of sifting through cosmic information at speeds and scales that defy human comprehension. It will act as the unrivaled pattern recognizer, detecting signals too faint or too complex for the human eye, the simulation engine capable of modeling entire universes in mere minutes, and the relentless anomaly detector, flagging anything that whispers of the unknown in the universe's ceaseless chatter. Consider the sheer deluge of data on the horizon. Future instruments, such as the Square Kilometre Array, or SKA, are designed to explore the universe with unparalleled sensitivity. This colossal network of radio telescopes spanning 2 continents will generate more data in a single day than the entire current Internet produces. To put that into perspective, imagine every single piece of information ever uploaded to the World Wide Web, every email, every video, every song, every web page, all produced within 24 hours, and then multiplied by a factor of 10, or even 100. Navigating such an ocean of information, searching for a single fleeting anomaly or a subtle pattern, would be utterly impossible for human teams alone. The artificial intelligence will become the indispensable navigator, the filter, the digital optic nerve processing this astronomical data torrent. This profound division of labor is precisely what will liberate human astronomers to do what they do best, what no algorithm can ever truly replicate, to exercise intuition, to ask creative and unexpected questions that spring from a deep human curiosity, to design entirely new experiments based on novel hypotheses, and, most crucially, to provide the vital context, the critical skepticism, and the philosophical inquiry that transforms raw data into profound understanding. The artificial intelligence provides the sight, but the human mind provides the meaning. It is the human brain that will connect disparate pieces of information, formulate new theories, and ultimately decide what truly matters in the grand cosmic narrative. We stand at a precipice of understanding. As we augment our own minds with this powerful new form of perception, as our senses extend through the tireless algorithms of artificial intelligence, a more profound and inspiring question begins to emerge. Not merely what new planet or new star will we discover, but what entirely new questions about the universe, questions we currently lack the imagination to even formulate, will we finally be able to ask. The ultimate discovery, empowered by this new symbiosis, might not be a distant world or an unseen galaxy, but a revolutionary way of seeing and questioning reality itself, unraveling mysteries we don't even know exist.